Named after the French mathematician Blaise Pascal, Pascal's triangle is also known as
The staircase to Mount Meru,
Khayyam's triangle,
and Yanghui's triangle.
We did it!
One way to think about Pascal's triangle is as a triangle where its zeroth layer is the number 1, and every subsequent layer beneath it is the number of paths that you can take to reach an element on that layer. So it sounds a bit confusing, but let's see a couple examples. So first of all, from the 0th layer to the first layer, there's one way that you can get to this element, so you write down the number 1. And then for this element, there's also only one way, so you write down the number 1. And that's the same for the second layer, one here and one here. But for the middling element, you can find 2 different paths to get to it, so you write down 2. So for the third layer, you do the same thing, 1, 1. And this time, there are 3 different ways, because there is 1 different path from the leftwards 1, and then 2 different paths from the rightwards 1. And you can see these different paths like this. 1 here, and 1 here. So same thing can be applied for this one. There are 3 different paths. And as you can see, it's basically just adding up the number of paths that it takes for the 2 elements right above whatever element that you're trying to find. So over here it would be 1. Over here it would be 1 plus 3, so 4. 3 plus 3, so 6. 3 plus 1, so 4. And there's only 1 path here. And you can continue this forever since Pascal's triangle is infinite. So 10, 10, 5, and then 1. So that's just one way to think about Pascal's triangle.
Let's see how we can use Pascal's triangle to expand a binomial expression. So as we all know, a binomial expression is of the form a plus b to the power of n, where a and b are both constants and n is a positive integer. So we want to set this up by writing down Pascal's triangle, which I've already done on the left-hand side. And basically what we can do with this is just have a little shortcut for doing this expansion. So essentially how this works is if you count the rows of the triangle starting from row 0. So if we call this row 0, 1, 2, 3, 4, etc., that will correspond to the power n, and you can use that to find your coefficients. So let's just use an example to illustrate this. So for example, if we pick like n is equal to 2, then you have a plus b to the power of 2. And if we start counting from 0, that's 0, 1, 2, so it's this row right here. And those numbers on that row is 1, 2, and 1. So this would basically indicate that it would be a squared times 1, which is just a squared, plus 2ab plus b squared times 1, which is still b squared. And we know that this is true, but if we just want to do this really quickly, this is how it turns out. And this is something that we already know. So yeah, there's that. And it also works for any other positive integer, although presumably you won't want to use it for numbers that are too large. But we can try this again with a plus b cubed. So that would be row 0, 1, 2, 3, so that's 1, 3, 3, and 1, so that's a cubed plus 3a squared b plus 3ab squared plus b cubed. So that's briefly how it works. Okay, and another interesting thing that we know about Pascal's triangle is that if you add all the numbers in each row, again, starting to count from 0, it corresponds to increasing powers of 2. So for example, at row 0, which is 2 to the power of 0, you have 1, which is obviously equal to 2 to the power of 0. You have 1 plus 1 on the next row, which is 2 to the power of 1. You have 1 plus 2 plus 1, which is equal to 4, which is 2 to the power of 2, and so on.
Another interesting pattern in Pascal's triangle is the powers of 11. If you take a look at every level, and you add together a decimal expansion of all of their digits, you end up getting powers of 11. So for example, 1 being 1 times 1, which is equal to 1. This being 1 times 1 plus 1 times 10. So the units place and the tens place, which is equal to 11. This being 1 times 1 plus 2 times 10 plus 1 times 100. So the tens place, or the units place, the tens place, and the hundreds place. You end up getting 121. For this, it would be 1 times 1 plus 3 times 10 plus 3 times 100 plus 1 times 1,000. And you end up getting 1,331. And if you can see these, you can maybe see that they're actually the powers of 11. So this is 11 to the power of 0, 11 to the power of 1. This is 11 squared, and this is 11 cubed.
Pascal's triangle also has geometric applications. So if we look at the numbers on this triangle diagonally, for example, at first you have a row of ones and then you have natural numbers. After that, you have what we call triangular numbers, since these numbers are the amount of dots, for example, that you can stack in a triangle shape. So we have 1, we have 3 here, and we have 6 here, we have 10 here, and so on. On the diagonal row after that, you have tetrahedral numbers, because in a similar fashion, you can stack that number of dots on each row, if you count it all together, to form tetrahedron.
A really useful application of Pascal's triangle is in combinatorics. The number of combinations when choosing a smaller group from a larger group correspond to coefficients of Pascal's triangle. For example, if you wanted to know the probability that out of 5 siblings, 3 of them would be boys, you would look for the 5th row, which is this one, and find the 4th element, which is this one. So there are 10 possible combinations of 3 boys and 2 girls. To find the probability, you just have to divide it by the total possibilities. So that's 10 divided by 1 plus 5 plus 10 plus 10 plus 5 and plus 1, which is equal to 10 over 32. So the probability would be 10 over 32. This is just another useful application of Pascal's triangle.